Hello everyone, welcome to our talk on MySQL backups at Booking.com. In this talk we will cover how we implemented backups at Booking.com and how we improved the existing situation that we have. The aim is to tell you how you can do backups on a large scale with a bunch of MySQL systems and so on, using freely available software, and to give you a bunch of techniques and design tools that you can use to implement this yourself. I'm Nicolai Plum. I work in the database engineering team at Booking.com. I've been at Booking.com for 17 years now in a variety of technical and back-end infrastructure roles. At the moment, I mostly wrangle the databases.
Hi, I am Peter Boros. I'm a principal architect in Percona's consulting team, and I helped Nicolai and achieve. Background is mostly performance tuning and automation and how to run things on larger scale systems. So let's see what we are going to talk about today. So first, we will check what people want from backups. Like why are we doing this at all, right? The database works without backups totally fine. Production is up. Why bother at all, right? We will talk about compliance and best practices. Then we will go through the previous setup of the backups, design features we didn't choose. Then we will move on to the setup that is in production right now and on the design features we did choose. And last, we will go through restore testing and reporting. Who is restore testing their backups right now from the audience? It's an important thing to do. We will talk about that. Okay.
So, question is, what do people want from their backups? You can ask people, what do you want from your backups? And they'll give you a bunch of answers. For example, they might say that what they want is they want backups of data. They would like long data retention. They would like, very precise scheduling to know exactly when the backups are happening. They'd like detailed reporting of exactly what's happening. And of course, they would like everything to be fully standards compliant and regulatory compliant and all the rest of it. But what do they actually want? What they want is restores. At the end of the day, people want to restore their data. They want to know they can get their data back. So the question a bit is, restore what? Because do they want to restore the backup to the latest backup? Do they want the whole backup with a point-in-time recovery? Do they want part of the database? Do they want part of the database with a point-in-time recovery? And do they want part of the database integrated with the current state of the database? This is a very tricky point, because if you have two databases containing, your transaction records and your customer details, and one of them is restored, what happens to the consistency with the other one? And if somebody screws up some code and nukes the data in a table and you want to restore that, what happens when you have the data about customers in one table but not the data in the other? And these are very difficult questions that we here do not have answers to because they depend strongly on the application. We can provide you with ways to make this easier. So the business view of backups tends to be, in case of trouble, they want the data back exactly as possible. Otherwise, they'd like to pay nothing for backups. So you have a cost optimization problem, but ultimately at the end of the day, this is about making sure that the backups really do work. And it's important to get that message across to your management, that this is an insurance policy that has to work. So one of the things you can do in this is you can have to look at compliance and best practices. And you can actually get some good ideas from auditors here. So auditors, if you ask them, or you ask your SOX auditors, what do we need to be SOX compliant with our backups, or the PCI auditors, or all the other auditors you might have, they'll say things like you should have a consistent backup policy, you should have detection of failures, you should have documentation of your backup design and processes and so on, and your backup data should be secure. The thing is, these things are actually good ideas. These are not just things that people put in processes because they wish to annoy you. So it happens to be that the enterprise design practices and regulatory practices actually match up quite well with what you really should be doing. So you shouldn't see audit requirements as some sort of massive obstacle to try to avoid here. You should actually try and go with them and see how that goes. Part of this is immutable backups, which is quite a hot topic lately because everyone is scared of being ransomwared. So the question is, could your own company? Who could destroy your own company here? Destroy all the data in a company. Excellent, you're a risk point there. We used to consider things like, we could back up to a worm disk. Like, I'll take the backups to a DVD disk. That can't be destroyed or by software and so on. You can get worm tapes, but they're expensive and bulky. And so what you want is like a worm drive, a DVD for the modern age. And you can do this actually on-premise with hardware, or you can even do it in a cloud. AWS and Azure will for you, and probably Google as well. And the basic idea is that the data is impossible to delete a preset amount of time, and then you can reuse the hardware so that you're not throwing away disks or tapes or whatever all the time. The basic idea is that you have, in our case, we have the Bacula director, which controls databases and storage daemons, and we'll talk about this design later. But the part we're looking at here is that we have local ZFS attached here, which is great for storing backups, but you can delete it. And we have, in our installation, a NetApp SnapLock, which is a software appliance where, with expiry time, you then cannot the data. You do need to make sure that you can't just go into the data center and take the disks out of the machine and put them on a fire. Behind the system at Booking, we ended up with a situation where we had these backups and nobody could destroy them. Because nobody had simultaneously access to all the database systems to delete all the online copies. So, like if you hacked me, you could delete all the online copies if things went really badly wrong. But you couldn't delete the ones in the storage unit. However, it turned out that I had a walk-up access pass to the data center, so I was the vulnerability here. Because I could delete all the data if I went mad and then pull the disks out of the system and set fire to them. So our data center manager actually asked me what the policy was for this. And I explained the design because I was very proud of it. And he said, "You're the problem here." And he pulled my access to the data center. And at that point, we had a reliable design system. So you have to consider that you yourself could be compromised here in this modern world where we can get hacked quite often. So let's talk about what we had in the past and what we are going to do in future. In the past, a backup system that worked, but it was very high effort. We took a backup every day. Somebody would check the backups had succeeded manually, and if something was broken, they would reschedule them manually and troubleshoot why this didn't work. If we wanted to add more storage, that was a pretty manual operation too. These things didn't provision themselves. And the thing is, at scale, something is broken all the time. So we needed to fix something every day. So this worked. It had a good success rate, but it had a very high workload. The sort of stuff we wanted in future was we wanted to reduce the manual action. We wanted to try and fix all identified possible failures now automatically, increase the automatic reliability of the backups and the tests, and we wanted to generate audit reports for the auditors without having to do a lot of manual work. So now on to the design features that we didn't choose. These are the stuff you shouldn't be doing.
Thanks. So some of these we thought through some of these and we did not choose it. So the first one is a single huge backup machine, right? It's very appealing to have a single huge machine, buy one with several terabytes of disks or have a huge instance. All backups go there. I know where it is. It can even be redundant. It can even be two large machines. It can have a huge storage attached to them. But this machine will be a bottleneck, both in terms of backup and restore performance and both in terms of reliability. Because if this goes down, every backup goes down, and they are gonna be invalidated. So the next idea that we didn't do is when the data flows through a single point. So often what people do is that they have a backup server, so to say, and then that backup server coordinates everything, and it coordinates a group of storage servers, right? And you can add more storage servers, but you have a central coordinator that can data flows through all flows through it. So practically, this can be the endpoint of the netcat where you pipe through extra backup or something like that. There are implementations like that, and we choose not to do it. Anybody has this? Backups flowing through a single point? No?
This includes if you have a single very large firewall there, by the way.
Okay. The next thing that we didn't choose is the copies of file systems, storing the file system copies inside file systems. So if you are running MySQL, you will have more than one file, right? You are probably running InnoDB file per table. You might be running partitioning, and you take care that you don't have too many file descriptors. Like, who knows the problem that you have tens of thousands of hundreds of thousands of tables in MySQL, and you start hitting file system bottleneck. You have this problem multiple. $140,000. So it adds up very, very quickly, and you will have this kind of file system bottleneck. Virtual tapes and other data grouping formats makes a lot of sense, but we are using Bacula, kind of a given. Not using virtual tapes avoid this kind of issue. So one backup will be one file on your backup system, or one backup can be multiple file by splitting the streams.
So the traditional enterprise solution will get a tape robot. This is a picture of one of the very large tape robots that Storage Tech makes. And people think, well, these things are industry standard, they have huge capacity, they're very durable, etc., and they're even on premises, so we've got control of our data. But the downside is that they're expensive. They're really expensive if you use worm tapes, because tapes these days are expensive items, and if you throw away the tape each time, the tape budget, I mean, it's even cheaper to use cloud storage to throw tapes away all the time. They're also large, which means you have to put them in your data center in a customized installation, custom power, cooling, floor space, etc. In a previous life, I worked for a telco where they had an IBM tape robot where you could add modules to the end, so you could extend this thing infinitely. But the problem was that after they've added about 15 modules, they reached the data center wall. And so they called IBM and said, hey, can you turn this thing round for us? And IBM said, sure, it'll take 3 days. And the database guys said, we can't survive without 3 days of writing tapes to this, writing database logs, to these tape storage. And I left the company before they solved that one, so I don't know what they did. You will also lose tapes, and there are many stories, fewer these days, probably because people are using less tapes, of, tape falls off the back of a lorry and so on. You cannot explain to the public and the press about cryptography and how the fact that you've invalidated the key means that this data on this tape marked big corporation can be decrypted. Like, you will never win this PR battle. So it's better just not to lose the tapes. Also, of course, tape is not in the cloud. And if you have an in the cloud strategy, tape drives is not it. So we didn't choose tape drives, and I'd fully recommend that you don't choose tape drives either unless you have some really specific requirements.
Yeah, in a previous life, I worked at some installations. They actually needed to make a hole in the data get the tape library in the building. So, okay. So let's talk about storage considerations. You can have binary backups and logical backups. We have binary backups, and binary backups are practically blobs, very large blobs. Encryption is extremely important. If the very large blob corrupted, you will go south. So using scale idea and has erasure coding is likely a good idea, and MinIO can do this from the more modern stack. So basically, what erasure coding does is it adds data to every chunk and make sure that the data is available. The important thing here is that if you are using a distributed storage as your backup storage, the replication factor and the durability are two completely different parameters that you can optimize for. And you have the backups because the important part of the data and the most important for them. So with backup, if you are running physical backups, like extra backup, snapshots, yeah, so most of the people. It's a lot less typical. Physical backups. What happens with HDFS if you back up to a distributed file system? That, for example, you have this purple database here. You save the first block. The purple block will be allocated on this storage node. The second purple block will be allocated in this storage node. The third purple block will be allocated on this storage node, and so on and so forth, right? So practically, most of the storage nodes will have data from most of your backups. What happens if one of these fail? All your backups will be invalidated. So if you're using a distributed storage to store very large binary blobs like database backups, make sure that you survive this scenario. Like if you have, let's say if you have a 600 node HDFS cluster with a replication factor of 3, in order for this to happen, you only have to have 3 machines failing out of the 600, which is not that much, right? So it's very important to take care of the durability if you are backing up to some kind of object storage or distributed file system. If you are backing up to S3, you are fine. It is also using erasure coding like that. For Bacula is storing data on virtual tapes. So one backup will be held by one storage node of Bacula, and in this case we are using different storage nodes for storing backups on a different day. So in our case, if a storage node fails, not all the backups will be invalidated, but we make sure that we have valid backups, even if it's from a previous day, in case any storage node fails. Yeah. It's coming. I will talk about that in detail. Okay. So another idea that we didn't do is non-temporal backup scheduling, and this is also very typical in larger scale systems. That let's say you have 2,000 databases to backup, right? Then the normal cron type of thing will not work very reliably anymore, and lots of people have the idea to not tie the scheduling to something temporal, but rather tie the scheduling to making a backup of everything. So let's do a backup of all 2,000. When it's done, whatever amount of time it takes, let's do a backup of all 2,000 again, right? This solves the problem nicely when your daily backup takes more than 24 hours. Like, who has a large database, a large legacy database, which takes a long time to back? Yeah. Well, more than 24 hours or a long time. If it's not yet 24 hours, it will be eventually, I guess. So this approach solves it nicely, but it has the advantage that your large database can actually starve your queue, can actually starve your backups. Okay. So let's talk about the current setup.
Right, so the setup that we have at the moment, the one that we have built, is divided into 3 layers. And these layers can be replaced, and they don't strongly depend on each other. So in the middle, we have the config generator, which is the part that was built new, which talks to a config database. We read in information from our server asset database to discover servers, and we'll talk about how we do that. We also have resource locks, because in some cases these are shared resources. We want to make sure that we don't take a backup that impedes some other activity, but we also want to make sure that other activity doesn't break our backup. And of course, user commands can come in. We can command backups or we can command restores. And the config generator drives Bacula, which is a third-party piece of software. There is an enterprise edition. There is also open software edition. You can also use Boros, which is a fork, and so on and so on. And you could also use a different component here, and we'll talk about that too. The backup sources that we use are that we take a copy of the database when it's cold. We shut down the database and take a copy. In theory, you can always pause writes on InnoDB, but historically this hasn't been super reliable, and we've decided not to try to analyze this problem in detail to solve it, so we just shut the database down. We have dedicated replicas for this, so we can do this. If you don't have dedicated replicas, you'll have to use some kind of online backup mechanism. And on each dedicated replica, we have an internal control API whereby we can cause the machine to shut down and take a snapshot, or shut down MySQL and take a snapshot, and we can take a backup from that, or we can clone it to a new machine. Yep. We're using LVM, basically. LVM snapshot works great. So you can shut the machine down, take the backup, and start it up again, but then replication can take quite a long time to catch up. It turns out that LVM can handle replication and reading out data at the same time. This is not tied to LVM. You could use a ZFS snapshot or any other snapshot that you wished. Or if your storage side supports snapshots, you could do that as well. The main point here is just to take a snapshot and start replication up, because that means things run better at the end. So the middle part, the config generator, which is mostly what we're talking about here, decides what backups to take, discovers backup sources. This is important. We discover dynamically that new sources are available by looking in our asset database and looking at our configuration data for new database chains and so on. Automatically allocates the storage, tracks the backups have completed or not, detects failure, Bacula reports a failure perhaps, also schedules and prioritizes, and we'll talk about prioritizing, retries, so it's failing backups, and it handles reporting and observability, and we will talk about all of these things. So inside Bacula, at the bottom bit, the actual data flow and data transfer here is done with a Bacula director, which is our bit that controls things in the middle. It has a catalog database where it keeps track of what's been backed up and so on. We have, our control plane, which is our commands that we wrote. We can also do backups in several places. So importantly, Bacula has the concept of storage daemons, which run on storage optimized servers. You can have more than one of these, and you can have them in different places. So here we have the director sending a command from the general network zone to the DSS PCI regulated zone, or any other regulated network zone you have, like if you handle health data or whatever. And it commands the transfer from the client on the database server to the storage daemon within the network zone, which means that the data doesn't leave the secure network zone, but you don't need to run two backup systems. One configuration across your secure general network zones. So over here we have another client being backed up to another storage daemon. Every time our PCI auditors show up, I pull out this diagram and explain it to them, and they go, yeah, looks good. So, you can be completely regulatory compliant with this one, because you can show the protocol is well defined, and you can point them at the Bacula manual that this does not transfer any actual private or financially secure or whatever data. It only transfers metadata. The storage hardware that we're using is a storage optimized rack unit that our storage team gave to us. 100 gigabit network, a big chunky CPU, because pushing data around is CPU intensive. Plenty of RAM because ZFS likes RAM. We're using big rotating disks to store the data. We're using ZFS. ZFS for several reasons. ZFS has a strong multi-disk RAID implementation. It also has absolutely paranoid checksums. As we said earlier, discovering data corruption is really important. We have different backups if this database is corrupted, but it's intolerable to restore data and not know about corruption. Disks are, as people will tell you, not reliable and lie to you all the time, so ZFS will protect you against this. We're using an NVDIM for the ZFS intent log for speed. You don't have to use an NVDIM, you can just use an SSD. Out of this, Bacula is doing the job management, queue management, actually scheduling jobs onto the backup host. It is not doing the choice of sources, the storage allocation, and the configuration here is generated dynamically by our control plane every time we need to change it, because most backup systems don't have a very good way to dynamically generate config and discover things. That's the sort of system integration work that you have to do yourself. So you can't get a backup system that will magically do exactly what you want. You tend to have to do some work there. The advantage of Bacula is that it turns out that writing your own job and queue management is quite difficult. Writing your own network transport is honestly a bit... So we use this as a building block, and we're not strongly dependent on it. We could swap in something else if you wanted to. Yeah. Yes, you can write the control plane software how you like. We'll tell you the best priority to choose later, though. Yep. We'll talk about that. Downsides of Bacula are parts of it are single-threaded. So there is actually a bit of a transfer limitation there, and that is something we might have to address in the longer-term future. You can parallelize on jobs. So if you have lots of databases, you can back these up just fine. If you have one giant database sticking around somewhere, data warehouse or whatever, backing that one up can be a bit troublesome, unfortunately. And changing the Bacula configuration is honestly a bit difficult. You tend to have to restart parts of Bacula and sometimes even interrupt existing backups to change the configuration. That's why we're not changing the config of Bacula very often. Instead, we are using the Bacula control interface to feed in command. It will tell us how we're doing that. So now on to much more engineering details of how this was done, because this is mostly the work done for us by Peter.
like Nicolai said, Bacula is a static system, and this part will be about how did we make it dynamic. So at the high level, it works. We get a list of things to back up from service discovery. Okay, it like what databases do you want to have backed up, and check what to do for each of them. So for each replication domain or for each replication chain, we check what to do with them. And there is only one question that we ask: do we need to make a backup right now? Yes or no? And that is decided by multiple questions, like is there a backup for today already, or the period of time for the period of time when we make the backup. So if there is a backup for today, a backup. Is there a backup in flight? So is a backup in progress already? If it's in progress, we don't do anything. You don't need to make a new backup. You need to wait for the one to complete or fail. Okay. What is the source of the backup? So we need to decide what will be the machine that will be providing the snapshot and will be providing the data for the backup if we need to take one. And where to put it? So what storage node to use to make that backup right now? And these questions at the high level are asked continuously. So it just never stops, right? And this is how this solution gets its resiliency, because we have this logic which defines what should be done, and it converges, the whole system converges to the desired state. And it's not just kicking things off one time. One bit is that the number of failures quite significantly, because you could imagine that on a large scale system like booking, a single machine not being available, it happens a lot, or a single machine going away during a backup, it happens a lot, right? But the amount of failures that needed to be handled manually went down very significantly as well, right? So embrace failures as long as you don't need to handle them, right? So as long as they are handled automatically. Okay. So for each chain, one or more backup jobs are needed, one per calendar day, one per location. So there are multiple availability zones, and if a database is present in multiple availability zones, there will be a backup in each. And if you want to make immutable backups, or normal, or both, right? So at the first run after midnight, the scheduling is calendar day based, but it can be whatever based. So you can have your base at 12 hours or something like that. At the first run after midnight, no chains will have backups, right? So that means for the whole infrastructure, all Booking.com databases in existence, right? We will discover the storage, we will discover the source, and submit the job to Bacula. And Bacula handles this well. Okay, there is no issue that Bacula gets overloaded, that Bacula gets into a bad state like this. The queuing at the Bacula and at the storage level, so those controls work really well. And this is what the expectation was from Bacula, that we could even kick off as many jobs as we want. You cannot kill it with just submitting jobs, right? Resiliency is there. And the submitting order of the backups is based on the size of the previous backups. And this is very important, because we are submitting by largest backup first. So what happens if you submit like that? your what your parallelism will look like over time will be the first one, right? So you need to do the largest first, and this can be counterintuitive, because you might want to say that you do the small ones quickly and you will have all the time in the world for the large one. But if you do the largest first, you will have the optimal utilization of the systems. While in random or doing chains in alphabetical order will lead to subpar utilization of the resources. Okay, so how do we find storage? So in Bacula, the storage itself is something static. So in the configuration, you need to spell out that this server, it's here. There is this server, it's here. So you have a list of servers at the end of the day. So we get the free space for each storage, remove the one that has yesterday's backups, and this gives us the resiliency that one storage server can die and we won't be without backups, or even multiple can die and we won't be without backups. Subtract the last backup size of the running jobs. So we get the free space. We know what amount of space the backup took took yesterday, and we see if it fits. If it fits, great. If it does not, we will find a storage node where it fits. And we just pick the one with the most free space that can have this backup. Okay, the advantages of this is that the failure of one storage node is not an issue, and no chain is without full backups, and adding storage nodes is relatively easy. And I have a graph about that. So I don't have the time or the dimensions, but here we decided that we don't have as much free space as we wanted. So we added 1, 2, 3 storage nodes to this subset of storage nodes, and the free space over time of all the storage nodes converge to this. So with this kind of scheduling, we have a very even utilization of storage space, and it really, from the user's perspective, it seems like a big pool, and you can just turn off a machine and you are fine. Now let's go on to restore testing. Okay, so this is very important, right? So if you don't test your backups, that's the project you should start tomorrow, because you actually have no idea if they are gonna work when you need it or not. Right? We all heard about incidents like this, that they had 3 backup methods configured, but none of them worked. So this is very, very important. So in this case, we say train like you fight. So test your restores with the same code and the infrastructure as you actually restore, and test every backup set. Test often, automate like that tomorrow, and have very good reporting, so you can spot the issues. So if you have restore testing failing, you should know about it, because a failing restore test, like a non-existent backup, it won't really trigger production issues. The project manager won't go and breathe on your neck like, when we have a successful restore test, right? Okay, and the restore tests are using Kubernetes. Who is using Kubernetes here for databases? And not that many people. So running the restore tests on Kubernetes is a very nice way to get yourself familiar with Kubernetes, and to put something on it that can use the resources dynamically. Yet it's not something in the production path, so it's a good way to introduce it to you. So backups are tested continuously on a very finite set of resources. So let's say we have this amount of CPU, this amount of memory, this amount of storage, in the Kubernetes infrastructure, and we can use that for restore testing as much as you want. And the restore tests are making sure that these resources are continuously utilized. And we are running as many restore tests as the resources permit continuously. So even if there was one yesterday, we will run it again if it can be run and the resources permit. So the next restore test to do will be the least recent one. So let's say we have 100 backups. For backup number 100, we did the restore test 10 minutes ago. For backup number 1, we did the restore test 3 days ago. Then we will pick backup number 1 and do the next restore test for backup number 1. Okay. And there is absolutely no error handling during the restore test. So containers are ephemeral. If they are failing, they are failing. That's normal. The last successful restore test timestamp will not be updated, and the job will be picked up again, and the new pod will be created, and we hope for the best. And it works. So, and everything is tested, like the whole set is tested in a few days' time. Okay, and we report on the age of the restore tests. So we report on what is the oldest restore test. So how does this work? So we have the control plane and the Bacula director, what are part of the backup infrastructure, and the Bacula storage daemon. And we have a Kubernetes cluster where we spin up a pod. That pod will have the Bacula file daemon, the client, the Bacula client, and it will have MySQL itself. So we restore the data to this MySQL from the Bacula SD. We start up the instance, and we can check it. We can check that MySQL instance that was started up dynamically in various ways, as much as we want. Right? And then the container can be destroyed, and we know that we recorded that backup was tested. That container can be killed, and we report that backup was tested fine. Yeah?
How big is this Kubernetes cluster? Like how many nodes?
It's a reasonable sized cluster, but it's shared with many other things inside Booking.com. So we're using a large shared BKS cluster that we have. For a reasonable sized chunk of databases, you can probably make do with something like 50 vCPUs and 400 gig of RAM, something like that. Oh, well, I don't know how many nodes there are in the cluster actually, like plenty basically. It doesn't really matter how you want to split things up. We also have the ability to pull data out if people want to restore it, because we were saying we test the same way that we'd actually restore. So you can connect a MySQL client or even a database replication client and pull data out that way if you want to examine what's been restored.
What does the restore testing entail? Do you read all the data, or?
Yes. It actually reads all the data from the backup. So it actually copies all the data to this container and starts MySQL on top of it. And then we have automated checks on this database. So at that point, it's a live database, right? And this system is, also usable by anyone. So if you want to have a MySQL with a specific backup, you can use this system to create an instance for yourself dynamically.
I was asking, once you restore to the container.
The question is, do we check every single record in the database? And the answer is no, we don't. We run some statistical tests on this. However, InnoDB itself has very strong checksums. So if your data is corrupted, InnoDB will throw you an error if you touch a corrupted page. So we scan a bunch of pages and check them that way. We have a consistency check that if the replica is not replicating up to date at the time we take the snapshot, it's not eligible to be used for a backup. So we check at the time we take the backup that it was up to date. Your auditors will ask you this question, and that is the answer. We do some random selects, yes, basically. We don't check every single page in the database, no. We do some selects, and that touches some pages, and if InnoDB has a problem there, it'll throw an error. We don't check differences between two backups. That's not really something that we would find very useful because the data has, of course, changed. We booked in more people to hotels. I'm sorry? This only they're generated automatically from a configuration database, so we don't need to back them up. And the config database is itself backed up. Like it's generated by Puppet, and it's generated by Puppet and some data from MySQL databases, and we back up Puppet repo and the databases so we can crank out a new config. Yes, we might take more questions at the end.
Let's speed it up a bit because we have very little time left. Reporting. A report goes to the ops team every day in the form of a Jira ticket, and if everything is fine, it's closed automatically. And we have some dashboards. One of the dashboards shows if we have backups, if we have the backups okay and the restore tests okay. And for the sake of this presentation, we made an error for you. So we stopped the backups for this test chain. So it shows up on the dashboard. And a couple of days later, we also screwed up the restore tests of it. On this dashboard. So this is the one interesting thing we have a dashboard about is backup times. So this is roughly a week of data. Again, there is no access, but each point here is a backup and the amount of time it took. So you can see that necessarily these are not the same chains every day, but that will be outliers. It depends on a lot of things like how the network is and not. But you can say that the days are going in and going out, and same, right? So the restore tests are not scheduled; they are done continuously, right? And it's very visible here that restore testing never stops. So we take the least recent one and try to test it, and we test many of them in parallel. Okay. Time is up.
Feel free to leave, but we'll continue slightly with things we could be doing in future. So there are things that we feel like we could do. Currently, I said users can connect to a restore container and take data out. Currently, that's not fully automated, so developers can't click a button and get a database container to look at the data from yesterday. Our aim is to do that because there are only a fairly small number of database engineers and a very large number of developers. Currently, the self-service is partial. We could use Oracle's clone plugin to get backups. The Oracle native cloning plugin is really, really fast. So it's much faster than Bacula at transferring data, so we might use that. We could also improve Bacula so that itself has better transfer performance. We could also provide data level export on this on the scope of a table or a schema within a database that has many schemas, because currently you can only restore the whole database. We could also use transportable table spaces via Extra Backup. There was a talk earlier describing how Extra Backup will give you table spaces in the exportable format. So you use Extra Backup, and it gives up a transportable table, and then people could restore data on a per table basis. Like I say, though, that's a very difficult thing to manage from your application, so your application developers have to be ready for this. So, well, thank you very much for coming. We've taken some questions already, but we should probably take any other questions later. Finally, if you'd like to work on all this, we're hiring. Choose your fate. You can work for Percona as a consultant, or you could work with Booking.com, just on Booking.com systems. Feel free to join us if you'd like to. Thank you very much.